Let's talk about probability. Start with an example. Fair coin is flipped 4 times. What is the probability of flipping 2 heads? Well, there's kind of a long way and a short way of doing this. The short way would be to say, I mean, they're the same, essentially. The probability of flipping 2 heads is the number of ways to get 2 heads divided by the number of ways you can flip 4 coins. So how many ways can we flip 4 coins? Well, every flip, there's 2 choices or 2 possibilities. You either flip the tail or a head. So for flipping 4 coins, there's 2 times 2 times 2 times 2 possibilities. We're going to list them all out in a second, but I don't want to right now. How many ways can you get 2 heads? Well, we're flipping 4 coins. We want 2 of them to be heads. There's going to be 4 choose 2 ways of getting 2 heads. Maybe the first flip and the second flip were heads, or the first and the third, or the first and the fourth, or the second and the third, the second and the fourth, or the third and the fourth. There are 6 ways of getting 2 heads, which is exactly 4 choose 2. So there's 16 total possibilities. And there are 4 choose 2, which is equal to 6 ways to get 2 heads. So this is going to equal 4 choose 2 over 2 to the 4th, which is 6 over 16, which reduces to 3/8. Now, this is kind of what I think of as the more efficient way of doing it. Trying to, as quickly as possible, count the number of things you want out of the total number of things. But we could have also listed the entire sample space, which would have been, well, there's 1 way of getting 4 heads. 4 heads. There's 4 choose 1 ways of getting 3 heads, or 4 choose 3 ways of getting 3 heads. You can get heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, or tails, heads, heads, heads. And then there's going to be 6 ways of getting 2 heads and 2 tails. Heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, and then tails, heads, head, tails, tails, head, tails, head, tails, tails, head, head. And then you can probably tell if there's 4 ways of getting 3 heads, there's also 4 ways of getting 3 tails. 1 way of getting 4 heads, 4 ways of getting 3 heads, 6 ways of getting 2 heads, 4 ways of getting 1 head, and 1 way of getting no heads. Right, this would be tails, 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 heads, tails, tails, heads, tails, tails, heads, tails, tails, or heads, tails, tails, tails. This would obviously be tail, 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 tail. So you could list them all out and then say, well, I want the probability of flipping 2 heads. Well, there's 6 ways of doing that. Out of 1 plus 4 plus 6 plus 4 plus 1 is 16 total ways of flipping 4 coins. So, oh yeah, we can see that it's going to be 6 out of 16. But I think it makes more sense to try and do it this shorter way if possible, right? You don't want to have to write all this out if you don't have to. Okay. let's continue with the example. All right. What about, what's the probability of flipping 3 heads or 4 heads? Well, again, we can go back to our list now. You could say either, well, the probability of flipping 3 heads is 4 choose 3 out of 2 to the 4th. Right, there's 4 ways of doing it out of 16 possible ways. Probability of flipping 4 heads is 4 choose 4 out of 2 to the 4th, which is going to be 4 choose 3 is 4 out of 16. 4 choose 4 is 1 out of 16. That's 5/16. Or you could look back at the work we already did. Say, oh yeah, there's 4 ways of getting 3 heads. There's 1 way of getting 4 heads. There's 5 ways of getting 3 heads or 4 heads. And there's 16 total possible things. So 5 out of 16. Let's actually keep this up for a second. Ah, come on. Feels a little better. What's the probability of flipping at least 1 head? So if you see this language, at least 1 of something, or at least a small number of something, this is usually a good indication that they want you to not make your life terrible. They're trying to give you an easier way of doing it. Instead of saying it's the probability of getting 1 head plus the probability of getting 2 heads plus the probability of getting 3 heads plus the probability of getting 4 heads, which we could do, right? The probability of 1 head is 4 out of 16. Probability of 2 heads is 6 out of 16. Probability of 3 heads is 4 out of 16. Probability of probably 3 heads is 4 out of 16. Probably 4 heads is 1 out of 16. And you could add that up, and 4 plus 6 plus 4 plus 1 is 15 out of 16. Instead, what we typically do is we say, well, the probability of getting at least 1 head is 1 minus the probability of getting no heads. Use the complement. And that's going to be 1 minus 1/16, which is 15/16. It's not always a guarantee if someone says at least this many, but often when someone says find the probability of at least this many things happening, it is often a good idea to say, oh, well, it's just all the possibilities minus the probability of it not happening. Kind of like the homework problem you guys have, where you have to find the probability of a committee having at least 2 people from different countries. And that's the same sort of idea, where you want to find all the possibilities and then subtract the possibilities where none of the people are from the same country on the committee. All right. Yeah. If you have questions, you should ask them. In general, but also about this. Questions about this? Doesn't seem like a terrible example. Let's do some more. We're definitely going to talk about conditional probability today, which I think you talked about in class. Okay. Let's do a couple more examples just to make sure we're all on the same page. So let's say you roll a fair 6-sided die. If someone doesn't say fair, the implication still is that the die or the coin or whatever is fair, but it's good to be precise. And we're going to let A be the event of an even number being rolled. So A is going to be consisting of either rolling a 2, a 4, or a 6. And B is going to be the event of a multiple of 3 being rolled. So B is going to be the event that we roll a 3 or a 6. So some of these are pretty easy to calculate what's the probability of A. Well, there's 3 ways of getting something in A out of 6 total possibilities. So the probability of rolling an even number is, not surprisingly, 1/2. The probability of rolling a multiple of 3 would be the probability, well, there's 2 different ways we get a multiple of 3, 3 or 6. 2 ways of getting what we want, divided by 6 total possibilities, it's going to be 1/3. So now the more interesting part, what's the probability of A intersect B? Meaning I want A and B to happen. Well, there's a couple ways to look at it. You can either just actually see what's in the intersection. So what's the only number we can roll where it's even and a multiple of 3? Something like 6, right? 6 is the only thing that's in both of them. So the intersection of these sets, or the overlap of these sets, is only the number 6. So this probability, well, there's going to be one way of getting what we want, the number 6, out of 6 total possibilities. Yeah, I feel like that's all. That's kind of the best. What about the probability of A union B? So when I read an intersection, I really do read it as an and. Meaning I want A and B to be true. And the only way we can roll a number that's a multiple of 2 and a multiple of 3 is to be a multiple of 6. On the other hand, this says I want A or B to be true. Meaning I want to roll a multiple of 3 or a multiple of 6. Well, that could be any of these. So it could be 2, 4, 6, or 3, or 6 again. So you could either just say, well, there are 4 ways of getting that. I roll a 2, a 3, a 4, or a 6. But I want to point out that there is a formula for this. And another way of calculating this is saying, okay, it's going to be the probability of A plus the probability of B minus the probability of their intersection. Because when you do A and B, you've counted the intersection twice. You can see this better if you draw a little Venn diagram. So in A are the numbers 2, 4, and 6. And in B are the numbers 3 and 6. And not in either A or B are the numbers 1 and 5. So if I want to find the probability of A union B, well, the probability of A is 3 out of 6. The probability of B is 2 out of 6. But I counted their overlap 2 times, right? I counted it once when I did A and once when I did B. So I have to subtract off the probability of A intersect B. So they only count it once. And that's going to be 4/6, which is 2/3. And this is a formula that comes up every once in a while. This is the usual version of it, although you could totally use it to calculate the probability of A intersect B, or you could do A intersect B over here and A union B subtracted over there if you really wanted to. It's kind of weird. No one ever does this, but you could say the probability of A intersect B is the probability of A plus the probability of B minus the probability of A union B. That would also be true, just stranger. I've never seen anyone write it that way, to be honest. Yeah, we got time. Sorry, I'm trying to think like how much more probability do we really want to do before we start talking about conditional probability? Hopefully everyone noticed that we've already done one of the homework problems you guys had to do, like the problem about the getting the 2 pairs. We did that one last week. So if you're having a hard time with that one, look back at the notes or the video from last class and take a look. You divide it by 6 because that's the amount of sides. Exactly, right? Because I'm dividing by 6 because it's the total number of possibilities. Another way to think about this is, again, if I want A or B, it's just the number of ways of getting what I want, which is getting 2, 3, 4, or 6 out of the total number of possibilities, which is 1, 2, 3, 4, 5, 6. Should I move on to conditional probability? Should we do? Yeah, let's move on. We can come back to this. So let's talk about conditional probability. And do you know, did he say whether or not you guys are going to talk about Bayes' rule or Bayes' formula? Is that a no, he's not going to talk about it, or no, he hasn't said? He hasn't said? Okay. It's usually something that gets covered, but I don't know how he would test you all on it if he hasn't had the time to get, because I imagine this homework that's due is your last assignment. So yeah, exactly. So yeah, he's probably, I can't imagine, usually they cover Bayes' rule. Oh, well, we'll see. I might cover it. So it is actually kind of a useful thing to know about. So I feel like I should give you at least one Bayes' rule example, maybe not today, but certainly next class, if not today. Even if you're not going to get tested on it or do any homework problems on it, I still think you should see it. Someone asked, yeah, so it's exactly the number of choices of what you want divided by the total number of possibilities. That's how you calculate the probability of a thing in general. So let's look at this next example. Let's say we draw 2 cards from a deck, from a standard deck. Meaning 52 cards in the deck, 4 suits, 13 ranks, et cetera, et cetera. What's the probability that the first card is a heart and the second card is a heart? And we'll talk about with and without replacement. So with replacement. So let's do it this way. Let's say that A is the event that the first card is a heart. And B is the event that the second card is a heart. And we want both A and B to be true. So we're trying to find the probability of A intersect B, which in this case is just equal to the probability of A times the probability of B. Now, this has to do with the fact that if we're replacing the card in the deck after we've drawn one, the first draw doesn't affect the second draw. And you draw a card, you look at what it is, and then you draw the second card. Whatever you did the first time doesn't matter if you put the first card back in the deck, as far as calculating the probability of the second thing. So what's the probability that the first card is a heart? Well, how many cards are in the deck? Did you say cards are hearts? How many hearts are in the deck? 13. How many cards? 52. So the probability of getting a heart on the first card is 13 out of 52, or 1/4 if we want to reduce that fraction. Put the card back in the deck. What's the probability that I draw a heart on my second card? Still 13 out of 52, right? Nothing changed because I put the card back in the deck. So the probability of the first card is a heart and second card is a heart. Sorry, I wrote 15 instead of 52 there. If you're replacing the card after you've drawn it, it's just 1/4 times 1/4, which is 1/16. And I should just point out that this is true if the events are independent. And there's a more formal definition, but the very general definition of independence is just if you know one thing happens and it doesn't affect the probability of the second thing happening, then the events are independent. Okay, what if we have without replacement? Well, now we have a slightly different probability. We're going to have the probability of A and B is going to be the probability of A, which is still going to be 13 out of 50, right? Draw the first card. There's a 13 out of 52 chance it's a heart. times, well, now the second probability is a little different. It's not just the probability that the second card's a heart, it's the probability that the second card's a heart, given that the first card was a heart, which is a conditional probability. It's a probability based on having some prior knowledge. So if the first card was a heart, how many hearts are left in the deck? What's the probability of drawing one of those hearts? 12 out of how many? 51. Right, because we already took one card out of the deck. So the probability of getting a heart, given that we already drew a heart, is 12 out of 51. There are now you could totally do this a different way if you wanted to, right? You could just kind of talk it out. You don't have to use all this language of conditional probability. You can say, well, I know there's a 13 out of 50 chance that the first card's a heart, and then if the first card's a heart, the second card being a heart, there's a 12 out of 51 chance, right? It's not like we're doing anything specifically fancy here, but it does help us kind of negotiate what's working here. We can simplify this if we want to. 12 and 52 both have a factor of 4, and 13 and 13 cancel, and you end up with 4 over 51. And I feel like I'm looking at something weird here. Oh, I forgot the 3. Apologies. I canceled the 4, was left with the 3. Sorry about that. 3 over 51 reduces to 1 over 17. I used to have a math teacher who would say his favorite prime number was 51 as a joke, because it's not prime. 51 is divisible by 3. So slightly less of a chance of both cards being hearts if it's without replacement, which makes sense, right? Because if you put the heart back in, you have a better chance of the second card being a heart. So this is kind of the idea behind conditional probability, is that if you're trying to find the probability of A and B, it's the probability of A times the probability of B given that A happened. It's the same formula here. It's just that the probability of B given A is the same as the probability of B, because knowing that A happened in this instance here with replacement doesn't affect the probability of B. So in this case over here, it's true that the probability of B given A is the same as the probability of B. Knowing that A happened doesn't change the fact that the probability of the second card's heart is still 1/4. It's still 1/4. Here it's different. And here the probability of B given A is 12/51. Interesting. This leads us to some formulas. There's probably 3 different ways people like to write these formulas. I'm going to show them all to you. So my preferred way of thinking about this is the following. I like to think about the probability of B given A as the probability of A intersect B divided by the probability of A. That's the way I like to think about it. But there are lots of other ways to write it. First of all, you can switch around the roles of A and B. So you can say the probability of A given B is again the probability of A and B divided by the probability of B. And then you can also solve for the intersection and say, I'm going to write the probability of A intersect B as the probability of A times the probability of B given A, or the probability of A intersect B is the probability of B times the probability of A given B. And I feel like these formulas make some sense in their language, meaning if I want to find the probability of A and B, it kind of makes sense that it's the probability that A happened times the probability that B happened if you already know that A happened. Or the probability of A and B happening is the probability of B happening times the probability of A happening, given that you already know that B happened. And the way I like to think about these formulas is again via a Venn diagram. If that's A and that's B, I'm trying to find the probability of B given A. What you're really saying is we already know A has happened. So I'm already kind of in this space here of A happening. If I want to find the probability of B given A, if I'm already in A, the only way I can also have B happening is by being in the intersection here. So it really kind of does make sense that, oh yeah, the probability of B given that A has already happened is, well, the only way you get B is by being in B and in A, but it's out of just being in A. I feel like that helps me see what's going on. Like, oh yeah, what probably B given A? It's just A intersect B divided by the probability of A. Let's look at some examples. It's been too high here. Sorry, my pencil. So let's look at this example. What's the probability sorry, this is written word. Find the probability that a card drawn from a deck is a queen given that it's a face card. And there's a couple ways to go about this. I kind of like to think about it as just, again, it's kind of the number of ways of getting what you want out of the number of things possible. So one way of doing this is say, okay, well, number of what we want divided by total number. All right, so how many cards are there that are what we want? How many queens are in the deck? 4. How many face cards are in the deck? 12, right? There's jacks, queens, and kings. There's 4 of each of them. 3 times 4 is 12. So the easier way, in my opinion, is saying, well, there's 4 queens, but if we know it's a face card, there's only 12 face cards. So there's a 4 and 12 chance. Or you could use this formula. You can say, well, if I say that probably A given B, where A is going to be getting a queen and B is going to be getting a face card, that's going to be the probability of A and B, or A intersect B, divided by the probability of B. So A intersect B, it has to be a face card and a queen. What's the probability of being a face card and a queen? Well, if I'm going to be a face card and a queen, what do I have to be? Can it be a king? No, I said and, right? Both things have to be true. Can I be a jack? No. Can it be an ace? No. How many cards are there that are face cards and queens? 2. There's a few more. There's 4, because there's 4 different queens: clubs, diamonds, spades, hearts. So, but I didn't ask for how many actually. I asked for what's the probability of getting a queen. So it's 4 out of how many? Right. The only reason I'm writing that is to show you kind of how writing this formula isn't terrible, but also feels unnecessary. All right, divided by the probability of getting a face card. So the probability of face card is the number of face cards out of 52, which is going to be 12 out of 52. And then hopefully you can all see those 52s are going to cancel right away. And you're going to get the same result, 4 out of 12, which is 1/3. Either way is fine. Usually, if I have the option to, I'm going to try and think about it in this first context. Meaning I'm just going to think, well, if I know how many things are in the given piece of information, I can just say it's however many of what I want out of however many there are that are given. Let's look at some more. So still 1 card from a deck. Let's now find the probability of a heart given that it is a 7. I'm going to do it what I'm going to dub the, I don't even know what to call it, what feels like the easier way to me. So given that it's a 7, all right, how many 7s are there? 4. So sometimes what we call this is the reduced sample space, right? My reduced sample space is the 7 of hearts, 7 of clubs, 7 of diamonds, 7 of spades. Right, that's what's my given sample space is, and given that it's a 7. And there's 4 things in it. All right, given that this is my new sample space, how many ways can I get a heart? One, only one. One way of getting a heart. So there's one way of getting a heart out of the 4 possibilities we have. That's it. That's my probability of A given B, if you will, of getting a heart given that it's a 7. Or we could do it the more formulaic way. We could say, all right, it's the probability of A intersect B divided by the probability of B. The probability of getting a 7 is 4 out of 52, or 1 out of 13. The probability of getting a heart and a 7 is, well, how many ways can you get a heart and a 7? 1, right? There's 1 7 of hearts and only 1, unless you're playing like gin with 3 decks or something. But we're not. We're playing with 52 card deck. There's 1 out of 52 ways. Oh, look, it's the same. No matter what way you do a thing, if you're doing it a different way, your answer should still be the same. So if you do it one way, you do it one way, you do it one way, you all should come up with the same answer, even if you do it using different methods. There's something I want to say about this. I will point out here that the probability of getting a heart in general is also equal to 1/4. Right there, or if you prefer, 13 out of 52. Right there, 13 hearts out of 52 hearts. And what I want you to see about this is that these events, A and B, are independent of each other. So A and B are independent. Knowing that B happened didn't affect the probability of A. Bless you. So we can say here that the probability of A is equal to the probability of A given B. Knowing B didn't change the probability of A. How would it differ if they weren't independent? Well, so kind of like in the previous example we did with the, sorry, 1 second. Well, in fact, this last example, the probability of the card drawn from a deck is a queen, given that it's a face card. The probability of getting a queen in general, right? So if we call A getting a queen, here the probability of getting a queen is 4 out of 52. Which is 1/3, 1/13, sorry, 1/3 up here. Whereas the probability of getting a queen, given that it's a face card, is very different than that. It's 1/3. So what I would say here is that the probability of A given B is not the same as the probability of A, which means that these are not independent. And that makes sense, right? If you know you've got a face card, that's going to drastically change the probability of getting a queen. Getting a face card and getting a queen are totally dependent events, or not independent events. How could we tell with a given problem? It's not always super clear. What I will say actually is this is how we check. So if someone ever asks you, are these two things independent? This is one way of checking. Is this probability equal to that probability? There's 2 other versions of this. You can also check the probability of B is equal to the probability of B given A, or you can check that the probability of A intersect B is equal to the probability of A times the probability of B. These are all ways of showing that 2 events A and B are independent. And usually the problem is it's not always 100% obvious. This one might feel somewhat obvious that they're independent because hearts and sevens kind of knowing that you had a heart, or sorry, knowing that you had a seven doesn't really affect whether or not you get a heart. That might seem obvious, that might not seem obvious. I don't know. To me, it feels obvious, but I also played cards for a lot of my life. It might not seem obvious if you haven't dealt with cards very much. Let's actually go the other way for a second too. What's the probability of drawing a king, which we'll call event A, given that we drew a club? Well, here's the way I'm thinking about it. I know the probability of getting a king in general is 1 out of 13. Right? There's 13 different suits, or sorry, 13 different ranks, and one of those ranks is kings. Or you can say it's 4 out of 52 if you want to go on. If you know you have clubs, well, then you're limited to the 13 clubs, and one of those is a king. So there's still 1 out of 13 ways of getting a king if you've got clubs. They're independent. Knowing that we had clubs didn't change the probability of getting a king. So you can either say, well, it's right, there's the probability of A given B, the number of ways of getting a king is 1 out of the 13 possible clubs. So 1 king of clubs out of 13 clubs. Or again, the longer way. The reason we talk about this, so like it seems to me that the shorter way of doing it always feels like the better way. Like if you can just be like, how many things are there and how many things do I want out of them? That feels easier. The problem is it's not always an option. Sometimes you really don't have the option of saying how many out of how many. Sometimes it's more percentages or decimals, and you can't just do this. But I could do it this way and say, oh yeah, the probability of getting a club and a king is 1 in 52. There's 1 king of clubs, and the probability of getting a club is 13 in 52. And that reduces to 1 in 13. So again, these events are independent of each other because knowing that we had a club didn't affect the probability of getting a king. And I'll just point out here so you guys can see it. It is also true that the probability of A intersect B is the probability of A times the probability of B. Again, that's not always true. This is true if they're independent. Probability of getting a club and a king is 1 out of 52. Probability of a king is 4 out of 52. Probability of a club is 13 out of 52. And oh yeah, a 4 and a 13 cancel out 52. Gosh, why do I keep writing 15 when I say 52? That's the second time I've done that. It's kind of weird. So yeah. All right, let's look at something a little more interesting. Enough of cards. Yeah, waste all that space. It's all right. So let's look at something different. Let's say we have a family, has 2 children. And we know that one of them is a girl. We call that event A. Girl doesn't have any names. What's the probability that both are girls? Now, you might say the probability is 1/2, and you'd be wrong, right? We don't know, right? It's not so easy to be like, well, there's one other kid, 50-50 chance of a boy or a girl. But the problem is we don't know which child is the girl. It could be the older child or it could be the younger child. So let's write out the sample space, or I should say really the reduced sample space. So our reduced sample space here is And some people like to write this as omega for sample space sub B for the sample space of B happening. You could either have girl, boy, boy, girl, or girl, girl. Those are the three ways you could have two kids where one of them is a girl. Right, you didn't get two boys. So the probability of, and actually, sorry, I should have written that as an A, right? Because A is my given. So we're trying to find the probability of B given A. Well, that's going to be, there's one thing I want, having two girls, out of three possibilities. So if you know someone has one child that's a girl and you don't know if it's the oldest or the youngest, you just know that one of their kids is a girl, the probability the other kid is a girl, that both are girls, is actually 1/3. Seems counterintuitive, but it actually is true. It's kind of neat. Stats is weird, but interesting. On the other side of things, and then right, I don't feel the need to do the long way, but if you want to do the long way, you say the probability of B given A is the probability of A intersect B over the probability of A. Probably if that both kids are a girl, well, there's one way of having two girls out of 4 different possibilities total. Right? You can have boy, boy, girl, girl, boy, girl, girl, boy. And then there's 3 out of 4 ways that one of them is a girl. Right here, I'm thinking about all 4 possibilities. So that top part is the 1 out of 4, and that bottom part is the 3 out of 4. Here's the difference. Another family has 2 children. And the oldest is a girl. What's the probability that the youngest is a girl? Well, now we have more information. Here, there's only 2 ways that can happen, that the oldest is a girl. Either the first child's a girl, the second child's a boy, or the first child's a girl, the second child's a girl. These other 2 ways of having kids don't apply. You can't have boy, girl, you can't have boy, boy. So here the probability of B given A, there's only one way of getting 2 girls out of 2 ways of having the oldest child being a girl. So it seems kind of funny, right? That this one seemingly innocuous piece of extra information changes the probability completely. If you know someone has 1 girl and they have 2 kids, the probability that they're both girls is 1/3. If you know which of the girls it is, like if you know they have 1 oldest girl and you don't know the other child, it's a 1/2 probability that it's a girl. It seems, again, it's a little, so I will mention in general, probability and statistics sometimes seems very logical and makes sense. Sometimes feels very counterintuitive. You're like, really? That makes sense? Okay, I guess. All right, let's see. What time is it? We got time. I keep saying until he runs out of time. So let's look at this one. A multiple choice test. I'm sure you won't be taking in this class. Has 10 questions, each with 5 answers. What's the probability of guessing all of them correctly? Okay, well, assuming that we have a 1/5 chance of getting anyone right. We were pretending like we didn't study for this test. We know nothing. We're just going in and filling out the scan for, excuse me. What's the probability of getting the first one right? 1/5. Probably get the second one right is also 1/5. And the third one and the fourth one, all the way to the 10th one. The probability of getting all 10 correct is going to be 1/5 to the 10th power, which is approximately way too small to take your chances on. It's about 1.024 times 10 to the -7th power. Very, very, very unlikely, but not impossible. On the other hand, what's the probability of getting 9 out of 10 correct? Okay, well, we have to get 9 correct, but we didn't say which 9. Right? It could be the first 9, right? We could be missing 1. So one way to think about this is it's the probability that the first one is incorrect, plus the probability that the second one is not correct, plus the probability that the third one is not correct, all the way to the probability that the 10th one is not correct. Right, so you get the first, you get the last 9 correct, or the first one and the last 8 correct, right? And each of these are different ways of getting 9 of them correct. And we want to find the problem, right? So again, we're trying to count up all the ways of getting what we want divided by all the ways of anything happening. Now, oh, can I go back a page? Sure. One sec. So on the previous page, we were talking about how, oh, cool. Got it. All right. So what's the probability of getting the last 9 correct and the first one not correct? What's the probability of the first one not being correct? Well, there's 5 possible answers. It didn't get it right, so there's a 4/5 possibility of that happening. But then the other 9, it did get correct. So that's going to be 1/5 times 1/5, right? 1/5 to the 9th power. And then the same thing's going to be true for the next one, right? Probably the second one not being correct is going to be, there's a 4/5, there's a 4 out of 5 chance of the second one not being correct. And then there's a 1 out of 5 to the 9th chance of the other 9 being correct. And I'm going to do this 10 times, which is going to be 10 times 4/5 times 1/5 to the 9th. Or as I'm going to write it, 10 choose 9 times 1/5 to the 9th times 4/5 to the 10 minus 9. So this is actually a formula. If you're trying to find the number of ways of getting so many things to be correct out of so many things, it's the number of ways of choosing, in this case, 9 things out of 10 times the probability of 9 successes. The probability of success is 1/5. The probability of 9 successes is 1/5 times 1/5, or 1/5 to the 9th, times the probability of 1 failure, or 10 minus 9 failures. So you can apply the same sort of formula to a much, I don't know, not less easy, but for example, if I said, what's the probability of, getting 6 right? Let's say 7. Let's say 70% is getting a passing grade on this test. What's probably getting 7 correct? Well, instead of trying to be like, well, it's going to be 4/5 and 4/5 and 4/5, we're getting 3 wrong, and 1/5 to the 7th, we're getting 7 right. We can say, well, it's going to be 10 choose 7. Right, there's 10 choose 7 ways of picking which 7 we're going to get correct. And then 1/5 to the 7th, because that's the probability of getting 7 of them right. And then 4/5 to the 3rd, because that's the probability of getting 3 of them wrong. And that's it. I don't know if he's mentioned this formula. I think it's called the binomial formula. You probably don't need to know it. But if you ever have to take a stats class, which I imagine many of you might, this will definitely come up. This is a nice formula. How much time? I'm always checking the time. Okay, yeah. Well, let's go ahead and do this next one. So this is where we're going to start moving into an example of Bayes formula, because it's a good example. And it's one anyone going into the biological sciences should probably be aware of. So here's our sentence. It's a little lengthy here. A blood test for a disease shows a positive result, meaning you have the disease. That's, oh yeah, in 98% of the cases when the disease is present. In 6% of the cases, we get a positive result. When the disease is not present. Which is a false positive, right? You don't have the disease, but it became a positive. If the disease itself is present in 1 out of every 250 people, seems like a pretty high prevalence. Right? That's like a 0.4%. Let's find the following. What's the probability that a random person tests positive? Well, it'll be helpful if we name some things. So let's say that A is the event that the person has the disease, and B is the event that they test positive. I don't want to name other variables or letters for other things because they're complements, meaning I don't want to say that like C is the event that they don't have the disease. I want to say that a complement is that they don't have the disease. And B complement is going to be that they test negative. So I want to find the probability of B, right? Given no other information, what's the probability they test positive? So when I do a problem like this, I often like to use a tree diagram, meaning you have choices at each level. So person takes a test. They either test positive or they test negative. Oh, sorry. Yeah, you can go kind of way. They either have the disease or they don't. So the probability that they have the disease is 1 in 250. The probability they don't is the rest, which is 249 out of 250. And then from there, one of two things can happen. They can either have a positive test or have a negative test. So I'm not going to write probability of B though, because it's not just the probability of B, it's the probability of B given A. Right? It's already true that the person has the disease. Now we want to find the probability of B given they have the disease, which we know. The probability of a positive test given the disease, we were told is 98% or 0.98. And just for the sake of completeness, they can also test negative. So let me ask you all, what's the probability of testing negative given that they have the disease? Right. Because at each level, the probabilities have to add up to 100%. If you have the disease, there's one of two things that can happen. Either you test positive or you test negative. There's no other options. So if there's a 98% chance of testing positive, there's a 2% chance of testing negative. In a similar way, if we don't have the disease, we know there's a 6% chance of testing positive. And that means there must be a how much percent chance of testing negative? I think 94%. So now I want to find what's the probability of someone just testing positive? Well, that's all the ways you can get to a positive test result. So it's either going to be up here or over here where we have a B in the result. So the probability of a positive test result is going to be 1 out of 250 times 0.98 plus 249 out of 250 times 0.06. All the ways you can get a positive test result, either having the disease and a positive test result, or not having the disease and a positive test result. And that, if you calculate it, comes out to be about 0.0638. Pretty small chance of someone just having the disease. Okay. A more interesting question, though, is, and this is the question we really care about. Oh my gosh, come on. Is what's the probability of having the disease given that you had a positive test? And the assumption that people make, which is kind of incorrect, is that it's going to be close to 98%. Because, right, we certainly know that if you have the disease, the probability of a positive test is 98%. We're asking the opposite question. Now we're asking what's the probability of having the disease given that you had a positive test, not the probability of having a positive test given that you have the disease. That we know is 0.98. We want to know now what's the probability of having the disease given that you had a positive test, because that's the more likely piece of information we're going to have, right? If you think you have this thing, you're going to go get tested, and then you'll be like, oh, well, the test is positive. Oh, I have it. Test is negative. Great. So this is where we really have to use those formulas and say, well, the probability of A given B is the probability of A intersect B divided by the probability of B. Now we just calculated the probability of B, but I'm going to write it out because this formula does come up. So the probability of B, I'm really going to write it as the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement, which is called the law of total probability, if that matters at all. If you're trying to find the probability of something happening, this is A and this is B, and you're trying to find the probability of B, it's the probability of A intersect B plus the probability of a complement intersect B. Those two parts added together give you all of B. Either you're in B and you're in A, or you're in B and you're not in A. That's kind of the only options you've got. And then on top, we actually already have that part on the bottom. The probability of A intersect B is the probability of A times the probability of B given A. Now, even though we're writing out this formula, which is Bayes' formula, it's kind of neat to see that we've already got it in this tree diagram here. You can totally find all these things in the tree diagram. If you try to find the probability of A and B on the tree diagram, A and B is this probability times that probability. It's 1 out of 250 times 0.98. And in the denominator, probability of B, well, again, it's all the ways of getting to B. It's 1 out of 250 times 0.98 plus 249 out of 250 times 0.06. I didn't take the time to calculate because I was lazy. I do want to calculate that because it really is, it doesn't matter that you see what this is. So let's see what we got here. On the top is 1 out of 250 times 0.98. Don't love the phone calculator. Don't recommend it. So that's going to be approximately 0.00392 divided by what we found before, which was 0.0638, which ends up being about 0.06144. Very different than 98%. So it's really kind of interesting and important to recognize that even though the probability of having a positive test, given that you have the disease, is 98%, the probability that you have the disease, given that your test was positive, is only 6%. Right, I know it seems, again, a little counterintuitive. But the thing here is that this probability has more to do with how prevalent the disease is than the efficacy of the test. Right, this is all really, I mean, because what you're doing here is you're taking the probability of A intersect B here, divided by the probability of B, but the probability that someone even has the disease in the first place is only like 6%. So that's what's really going on here. It's this probability that's much more meaningful in this calculation, which is kind of interesting. But also, I mean, that's a hard question to answer. I'll give you 1 sec. What I'll say about this is something that actually comes up in real life, right? When people are told about how effective a test is at telling you something, they're really having to do this type of calculation to make sure that you're telling your patient the right kind of information. And just because you tested positive for this thing doesn't mean you 100% have it, and you should probably test again. Because the chance of a false positive is fairly likely. In fact, the chance of a false positive and the chance of a complement given B is pretty high. In fact, we could calculate if we wanted to. I want to say it's the complement of this, but I don't think that's actually the case. Well, I feel like it should be. Yeah, it should be. This is definitely going to be about 93.9%. That's not a false positive though. False positive is getting a positive result given that you don't have the disease. We're talking about not having the disease given that you have a positive test. So, right, even if you have so that's right. So again, just language things, right? False positive would be the probability of a positive test given that you don't have the disease, which is about 6%. It's actually, we were told it was 6%. Whereas this is the more important piece of information here, right? This is the probability that you don't actually have the disease given that you had a positive test. So, right, even if you have a positive test, you're like, oh, there's still a pretty good chance I don't have the disease. I should probably take another test. And that's usually the case.